think about how you actually use these models. You send a long system prompt full of instructions, or you paste in a big document and then ask 10 different questions about it. Or you hold a long conversation where the whole history rides along on every new turn. In all three cases, something wasteful is happening under the hood. Every single request, the model reads that entire repeated chunk again from scratch, doing the full expensive work of processing thousands of tokens it already processed a moment ago, just to get back to the one new thing you actually added. You are paying in money and in time to reread the same pages over and over. Prompt caching is the fix, and to understand it, we have to reach back to an idea we met when we talked about memory, the KV cache. Quick note before we dig in. If you find this useful, subscribe and drop a topic you want explained in the comments. Now, let us get into it. Here is the whole idea in one sentence. Prompt caching is an optimization where the model saves the internal state it builds while reading a stable part of your prompt, and reuses that saved state on later requests that begin the same way, so it skips rereading the repeated part and only processes what is new. To see why that saves so much, remember what the model is actually doing when it reads. Back in episode 9, when we counted what fills your memory, we met the KV cache. When a model reads your prompt, it does an expensive first pass called pre-fill, where it processes every token and computes a set of internal values for each one, the keys and values that attention uses. Those computed values are the KV cache, and normally they live only for the length of one request and then vanish. So the next time you send a prompt that starts with the exact same words, the model throws away all that work and computes it again from zero. Prompt caching says something obvious in hindsight. If the beginning of the prompt is identical, its KV cache is identical too, so do not recompute it. Store it, and on the next request that shares that prefix, load it back and jump straight to the new tokens. You compute the shared part once and reuse it again and again. The payoff comes in two forms. The first is cost. Providers charge dramatically less for cached input, on the order of 90% off the normal input price for the part that was a cache hit. The second is speed. Because pre-fill is often the slowest part of answering, especially with a huge prompt, reusing it slashes the time to first token, the delay before the model starts replying. Less money and a faster first word. Now the real mechanics, because the three big providers do this differently, and this moves fast, so treat the exact numbers as a snapshot. Anthropic uses explicit caching. You mark where the cacheable part of your prompt ends with a cache control breakpoint, and you pay a small premium the first time to write it into the cache, then a deep discount, around 1/10 of the normal price, every time you read it back. OpenAI does it automatically. Once your prompt's stable prefix crosses a length threshold, it caches it for you with no code changes and bills the cached portion at a reduced rate. And Google's Gemini offers context caching in both an implicit automatic form and an explicit form you control, with a small storage fee for holding the cache over time. Different controls, same core idea, reuse the pre-fill. And this hands you one concrete design rule that ties straight back to episode 10, prompt engineering. If reuse depends on the beginning of your prompt being identical, then you must put everything that stays the same at the front and everything that changes at the very end. Your fixed system instructions, your big reference document, your tool definitions, all of that static content goes first, so it forms one long stable prefix that caches cleanly. The user's actual question, the one thing that differs every time, goes last. Structure it that way and almost your entire prompt is a cache hit on every call. Structure it backwards, with the variable part up top, and you poison a prefix, so nothing after it can be reused and you pay full price every time. Same words, but the order decides whether caching works at all. So how does this land depending on who you are? As an individual, you mostly get this for free. The assistant apps you use lean on caching behind the scenes to answer faster in a long chat, and you feel it as snappier replies. As a startup, this is one of the highest leverage cost levers you have, because if your product sends the same big system prompt or the same document on every request, caching can cut your input bill by most of it almost overnight, and the only work is ordering your prompt correctly. And as a large enterprise running high-volume workloads, caching is core infrastructure. The difference between an application that is affordable at scale and one that is not, and it rewards designing every prompt around a long, deliberately stable, shared prefix. So let us bring it home. Every request normally rereads your whole repeated prompt from scratch, recomputing a KV cache it already built before. Prompt caching stores that pre-fill and reuses it whenever a later request shares the same prefix, cutting cached input cost by roughly 90%, and sharply dropping time to first token. Whether through Anthropic's explicit breakpoints, OpenAI's automatic caching, or Gemini's context caching, as long as you keep your static content first and your variable query last. We just made the model reuse the work of reading. In the next episode, we go after the other half of the cost, the work of writing, the slow, one token at a time generation itself. It turns out you can make a model generate several tokens in the time it normally takes to make one, with zero change to the output, using a beautiful trick called speculative decoding. That is where we go next. Content, that is the core of it. If this helped, hit like and subscribe, ring the bell for the next deep dive, and tell me in the comments what you want broken down next. Thanks for watching.